Thank you guys for being here, as well as MD Publishing, WBA, and the great vendors for sponsoring these regional events. I think it's probably some of the best value-added continuing ed you can give yourself. And I've come to really, truly believe too that these events, coming to these things, almost has a psychological, therapeutic benefit as well. I mean, just getting together with like buds, decompressing a little bit, I think it really has a way of just helping us kind of reaffirm and recharge our emotional batteries, so you can go back, back onto the job the next day and kind of be renewed and kind of just realize the importance of what we're all about and what you guys are doing on a regular basis. I think some of the emotional benefits, and it really became apparent during the COVID years, especially when MD Publishing was putting on these things when everybody else was shut down, when you guys were kind of going nuts. And coming to these things had a way of just kind of rebalancing the teeter-totters a little bit. So I'm just glad we're all here. Anyway, what I want to kind of touch on here are just some of the fundamentals and differences between blood pressure measurements. One of the things, I was in healthcare for 20 some years before I got into academia, and I distinctly remembering multiple times there were differences between an invasive arterial line pressure and what the clinicians and nurse was getting with a cuff. And more often than not, they would believe the cuff rather than the art line and the monitor. And I really didn't understand a lot of the nuances and the differences to adequately explain why that might have been. So the more I just continually believe, the more we can kind of get into their world and understand what they're up against clinically, therapeutically, the better off we are able to support them and help them in their overall mission. Yeah, good, okay, yeah. Anyway, so what we want to touch on is just some of the fundamental stuff, and some of these things you guys already probably know intimately, backwards, sideways, and forward, but hopefully there'll be maybe some new pieces of material in here that might fill in some gaps or reinforce what you already know. But fundamentally, where blood pressure comes from and the effects on where we take these pressure measurements. Also, we'll touch on some of the fundamentals associated with the standard auscultatory or stethoscope and cuff methods, the oscillometric or the non-invasive machines that we use, and direct measurements, and the effects of the stopcocks, the tubing, the air bubbles, and all those kind of things that go into potentially influence how these measurements are actually made. If you go through, there's just a ton of literature in the medical literature on obviously the importance of blood pressure measurements, but even among physicians, they're out there actually quite critical. Many of these papers over the years, decades, are really quite critical of how kind of sloppy we tend to take these measurements despite their importance. And you're putting people on medications for high blood pressure, you're treating high or low blood pressure with very powerful vasoactive drugs, and based on these numbers, which sometimes can be dramatically off. And we'll touch on how and why some of those things happen. So fundamentally, you kind of have it down, and there's a whole variety of different ways in which the circulatory system can be illustrated, but some of these schematic things can be really kind of conceptually helpful. But the heart obviously is 4 chambers, very, very tightly and exquisitely synchronized to pump blood through both the body from the left side of the heart, and also simultaneously an equal amount of blood, 50 mLs or so, shot glass and a half, if you're into that kind of thing, somewhere in that general volume. It's a pulsatile pump. And what we'll touch on a little bit also, we'll see that the blood leaving the left ventricle, entering the aorta, and many of the great vessels after that are elastic. Generally elastic, and the younger we are, the more elastic they tend to be, and we'll see the effect and the influence of those elastic nature of the arteries in a bit here. As the arteries get smaller and smaller and smaller, branching down, they become what are referred to as arterioles, and at the level of these arterioles, there's actually small bands of smooth muscle that surround. There's actually smooth muscle throughout all of the arteries, but at the level of these arterioles, there's little bands of smooth muscle that are under central nervous system control. And they behave almost like hose clamps. So if the body, for whatever reason, might not need as much blood going to a particular capillary bed or particular organ, it can basically throttle down, increase this, pinch the arterial off and reduce blood flow to that part of the body. And conversely, if it needs more blood flow, it can relax the clamp and increasing blood flow to that capillary bed. And ultimately, the whole point of the whole system whole cardiovascular system is to get nutrients and oxygen to the respiring cells. The cells are out here. Every cell is close to a capillary. In fact, there's so many, we have thousands of miles of capillary. It's just kind of an unimaginable concept. Estimates I've seen have been like 20,000 miles of capillary. Every cell in the body has to physically be close, relatively close to a capillary. Otherwise, it's not going to get fed, become hypoxic, won't get oxygen. And the cells, of course, produce waste that they have to get rid of. So everything is designed to bring blood, nutrients, waste, and get rid of waste at the level of the capillary. Another way of kind of thinking about blood pressure, again, you can think of the, in this case, just the left ventricle as basically a pump, a piston pulsatile pump. With each beat, it's ejecting a bolus of blood, again, that 50 mLs or so. And the aorta, being elastic, and we'll see what the effect of that is, it actually produce some hydraulic filtering in effect, in a sense, but blood flow, which is cardiac output, and going through a resistance produces the blood pressure. So our mean pressure is really, and it's very analogous to Ohm's law. If you guys, the Sparkies are all, you burned into Ohm's law, voltage, current times resistance. Current is analogous to cardiac output, and the arterial resistance, the net resistance is resistance. So the product of those two is what produces that pressure. I don't know if you guys, maybe Dave, you guys might see it in open heart surgery. I distinctly remember seeing surgeons, thoracic cardiac surgeons, before they would start, they bypass, they would palpate the aorta. I don't know if you've ever seen, maybe sometimes you'll see the surgeons do that. And what they're trying to feel, because especially in elderly, older people, the aorta becomes stiffer. The older we get, we lose elasticity in these elastic arteries, and actually they can become calcified. So if before you put somebody on bypass and you cross clamp aorta, if you've got a whole layer of calcium, calcification in that aorta, you could just create all kinds of crunchiness going on in there with the clamp. So the elasticity plays a key role, which we'll see here in a bit. Okay, but the arterial pressure waveform, and this is what we typically see in the ICU and the ORs on our monitor, is this top waveform here. That's the conventional arterial pressure waveform. What we don't often see, because it's not easily measured at all, is the pressure, in this case, just the left ventricle. So the pulsatile pressure leaving the, actually inside the ventral, you can see it almost goes to zero. It'll go up to a peak pressure, which we'll see is our systolic pressure, and then it actually very quickly falls almost close to zero again. So it's very pulsatile in that nature. You can see a very, very large, we call this dP/dt, change in pressure with time. So this is a measure of how strong the heart is. The contractility of the heart creates that real positive, sharp upsurge there. Okay, and if you remember, you guys are Sparkies at heart, right? From your basic circuit somewhere. Okay? Half-wave rectifier, you remember that kind of? Just a simple diode and a resistor will produce a half-wave rectified signal. And if you just look at the two, you can kind of see how that filtered half-wave rectified electrical signal is kind of loosely similar to the arterial waveform. And what that all points to essentially is that the filter capacitor in the electrical circuit is analogous to the elastic nature of the aorta. So the aorta and the elastic arteries are basically a form of a hydraulic capacitor, filtering those large pulsations from the ventricle. Okay? That kind of you can kind of think of it loosely like that. And also in the same kind of electrical vein and analogy is that just like current flows down a voltage gradient, potential, so does blood flow down a pressure gradient. So at the level of the aorta, right out of the aortic valve, the pressure is the highest. As it flows down through the arteries, arterioles, it gets smaller and smaller. capillaries, venules. This is where the veins, capillaries become small veins, venules, and then they become larger veins. And then ultimately, the inferior superior vena cava enter into the right atria. And so the pressure at that point is not zero, but it's only maybe a few millimeters of mercury. By the time the blood gets all the way back to the right heart, pressure is dramatically reduced. And this is at the level here, we refer to that as central venous pressure. So if you ever hear clinicians talking about a CVP, this is what they're kind of talking about. And that can become elevated in certain disease states. That can be an issue. But fundamentally, it's relatively low by the time the pressure gets back to the heart. The pulsations also diminish as we move farther and farther away from the heart. The arteries are becoming less and less elastic, becoming more and more rigid. So by the time we get to the level of the capillaries now, the pulsations are virtually gone at this point. So the blood flow by the time we get to the level of capillaries is relatively continuous at this state. Although it leaves the heart very pulsatile, by the time we get to the capillaries, not only has it slowed down dramatically, but it's also relatively smooth. I kind of liken the blood flow of the level of the capillaries as like a freight train hauling ass out of the aorta, and it gets down real fast, and once it gets to the capillaries, it slows down, and it's at the level of the capillaries is where the waste is being loaded on, nutrients are being offloaded. So in a kind of crude, gross way, you know, you got your food and your waste in the same car. That's kind of what's going on. I mean, the cells are depositing their waste products, taking on nutrients, but it's all going on in the same blood, volume of blood. So you can see what happens to the blood pressure at this point in the capillaries, down to maybe 20 millimeters of mercury or so. This is also one of the reasons why patients that are bedridden and without being moved are more prone to bed sores, decubitus skin ulcers, because the pressure in those capillaries is so relatively low, it doesn't take a lot of sustained forces to pinch off those capillary beds and end up with necrotic tissue. Pressure's kind of low at that point. Okay. Another kind of cool, again, illustration here kind of reveals how the heart, you can kind of think of the heart, if you're still with your electrical, you remember your constant current sources and parallel resistor networks, Kirchhoff's current law. You know, sometimes that initials a post-traumatic stress response in some people. They can't stand hearing that stuff. So, but anyway, if you think of the heart as kind of a constant current source with, say, a resting cardiac output flow, 5 liters a minute or so, the body in its wildly infinite wisdom will suck off amounts of that flow depending on the metabolic needs of its various organs and tissues. So that 5 liters, for example, is going to get divided up. Some of it's going to go to the brain, some's going to the heart. The liver is a big hog, takes up a good 27% resting blood flow. Kidneys takes a ton, muscle, and depending on, you can think of each one of these organ systems as kind of a variable resistor, you know, a potentiometer, depending on what the needs are. So if you start running up and down the stairs, skeletal muscle needs more blood, so it's going to open up, get more, it's going to divert blood flow to where it's needed. That's where the fight or flight sympathetic nervous system response comes from too. If you're under attack by a major gorilla or a crazy person at work, the nervous system can't tell the difference, you know, between some asshole boss you're working for and a gorilla coming at you. It'll have, you can initiate those responses. But so what it would happen then under sympathetic, muscles get stimulated and we would cut off blood flow to the stomach, gut. You know, body saying, I don't care about digesting food, you got to get out of here. So it'll automatically adjust depending on your needs. But blood pressure, as the kind of the term name implies, it's a force, circumferential force within the blood vessels divided by the area, is what that is all about, force over area, just from basic physics. And of course, in our country, yes, we typically refer to those pressures in terms of millimeters of mercury, but they are equivalent in a whole variety of other units as well. you wouldn't want to go to your, say your blood pressure is 1.9 psi. Well, if someone did, well, okay, that'd be 100 millimeters of mercury. Okay, what we're getting back to, the actual arterial waveform, there's a number of nuances here and specific things associated with this waveform. Again, this is what you typically see with an invasive arterial line in. We'll touch on those here in a bit. But the difference between the systolic and the diastolic pressure is what we call the pulse pressure. And this is analogous to the peak-to-peak ripple in a power supply. If you got a little bit of AC riding on a DC signal, that would be that peak pulse pressure. We have two phases, typically in our cardiac cycle: systole, which is the working, more metabolically active of the phase, and then diastole is the relaxing, filling phase of going on in the heart. And the wildly cool thing here, you notice how diastole is about almost twice as long as systole. It's during diastole, and only during diastole, that the heart is getting its blood. When the heart is giving blood to the rest of the body, during systole here, there's so much tension in the myocardium, the heart wall itself, that it basically pinches off the coronaries. So the heart is basically being starved for blood, not totally, but mostly during systole, and then during diastole, when it's in its relaxation filling phase, now the heart is being perfused during diastole. It's kind of a cool thing you think about, that you're kind of working only 8 hours a day and you're sleeping for 16. Kind of a cool thing for a heart, it's got to keep going for a while to give it that kind of rest consistently. Because of that, because the heart spends more time in diastole than systole, the mean pressure, we estimate it and calculate it a little bit differently. You just never want to take the arithmetic mean. So you wouldn't take 120 plus 80 divided by 2. Don't ever want to do that. Because again, more time in diastole than systole. So we use a little bit of a formula. We take the diastolic pressure plus 1/3 of the difference of the pulse pressure. In the actual monitors themselves, we do it a bit more mathematically precisely. We'll take the actual area under that curve and compute the mean that way. Some of you guys work on the balloon pumps, aortic balloon pumps? Yeah, and that is a really wildly credible therapeutic device. And what that pump fundamentally does, two major things that give it its wild therapeutic value, is that we advance this big bratwurst-like balloon up the aorta, or descending aorta here, and right at the closure of the dicrotic notch, ideally, right when the aortic valve slams shut, we want to inflate the balloon. Typically using helium, low mass gas, we can very quickly blow that balloon up. And in the process of doing that, what happens is that we're going to augment or artificially increase momentarily the diastolic pressure. And why that is significant, because you see the outflow, on the outflow side of the aortic valve, the inlets to the coronaries are on the outflow of that valve. So anything that would momentarily jack that pressure way up, which that balloon does, blows up like that, it's going to increase the perfusion of those coronary arteries. And then obviously right before the next systole, you don't want that balloon inflated, and the ventricle is going to try to eject. That would be bad. But what we do right before ejection, we deflate the balloon. And that does a massive reduction in what we call afterload. So it takes a tremendous amount of effort away from the heart. It's just kind of loosely-goosey, like opening that door. If we're the ventricle here, at the very same moment I pushed on the door, somebody on the outside pulled it open. The amount of effort I would have to exert to open that door is dramatically reduced. So if you're a sick, busted up heart, you don't want to have to be busting ass trying to get blood out through the door, through the valve. So the balloon pump does a wild job at reducing afterload and increasing perfusion to the coronaries. Okay, and fundamentally, this is what we're after. This is clinically, all of this stuff ultimately is about How do we get systolic pressure and diastolic pressure? That's the goal. And there's a whole host of reasons for that, clinically and physiologically, why we want to know that. The peak pressures tells us about the strength of contraction potentially of the heart. Elevated levels of blood pressure over time are not good for the brain, can contribute to strokes and heart attacks. Also just beats the snot out of the kidneys. Long-term high blood pressure does a real serious damage to the kidneys. Kidneys need a lot of blood flow, as you saw in that one diagram, good 20% of the heart's blood flow for the kidneys to work. And that's one of the other reasons the kidneys are relatively high up in the chest cavity. We get a lot of blood flow that way, and it needs a lot of pressure. If we lose blood pressure, kidneys are often one of the first organs to start feeling that. Diastolic pressure again, reflects arterial resistance, and fortunately, mean pressure stays relatively constant. There's not as much fluctuation, in other words, as in mean pressure. So if you've got some serious vasoactive drug titration things you're doing, the mean pressures tend to be a little bit more useful clinically for that. Whole host of things that affect our blood pressure, fluid volumes, of course. If you have high blood pressure, the thiazide diuretic drugs are often what's prescribed first to try to bring blood volume down. You bring blood volume down, we bring pressure down. Heart as a pump, resistance of the arterioles, veins. All of these things, the body is constantly adjusting, balancing, and they all contribute to blood flow. Okay. Another wild thing that happens in the body, and not as much elsewhere in other physical systems with rigid tubing, is this concept of pulse wave amplification. So when the, and it almost seems kind of paradoxical in a way that how can the pressures be higher, let's say, in a femoral artery or in the brachial artery than they are at the aorta when they leave the body. And part of that fundamentally is, as the pressure wave is leaving the heart, the ventricle, if any time it runs into a mismatch, a fluidic impedance mismatch of sorts, where maybe coming to a bifurcation, two vessels going off, changing in diameter, it alters the impedance, the fluidic impedance, if you will. So we get reflections of that pressure pulse coming back and adding or subtracting to the forward going pressure waveform, and that can create artificially larger pressures in the extremities the farther we get away because of that pulse wave amplification. And it's potentially more pronounced the more compliant the arterioles get. Okay, now fundamentally, the whole point of this whole talk basically is to look at these differences. So we have two fundamental indirect methods of blood pressure. And I don't even like using the word measurement because we're going to see here shortly that's almost a misnomer. The cuff, conventional cuff, refer to the auscultatory method just simply because we're listening with a stethoscope. We use a stethoscope to listen to lung sounds, bowel sounds. Those are all auscultatory, sound-based tools. And the oscillometric method with our Dynamaps and our general machines are also indirect measures. Collectively, they're referred to as sphygmomanometry. The key thing, though, is keep in mind it's an indirect measure. We're going to see what fundamentally the effects of that are, but oftentimes we'll use the brachial artery of the upper arm, medial side of the upper arm. You can see the big brachial artery here. That's where the cuff is going to be surrounded. We can use other, because this is convenient mainly, other sites. You may see the forearm or the wrist. You see some of those wrist-based blood pressure monitors. I've always been really, really skeptical of those because of the pulse wave amplification. There was even some devices out there years and years ago. They used a finger, basically had a small little cuff on a finger trying to get a blood pressure from a finger vessel. Again, theoretically, it should be possible, but the pressures just physiologically, physically are different dramatically, can be dramatically different the farther out we are. But the conventional approach, and again, you have this probably down, put the cuff around the upper arm, and the cuff will typically, the clinician will typically inflate that cuff to a pressure much higher than they suspect your systolic pressure to be. And in the course of doing that, they're going to completely occlude, pinch off blood flow in that brachial artery. If you ever get a chance to mess around with the machines, and if they got a pulse ox on it too, you can see the pulse ox waveform. Put the pulse ox probe on your same arm as the cuff, pump up the cuff, and you'll see your pulse ox waveform. Yeah, and it's just because you've basically pinched off blood flow completely to that artery. Because again, it's that circumferential force created by the cuff is pinching that vessel shut. Cuff is pressure will be gradually, slowly released, and in the course of doing that, that backed up blood now is going to come flying through this partially occluded vessel at a much higher velocity. Okay, and flow is equal to area times velocity. So if we got a small area, we're going to get a lot more velocity, and that higher velocity is going to create turbulence in that vessel, and that turbulence creates vibrations that can be heard as the classic Fennigkoh sounds from the stethoscope. So it's that turbulence creates the vibrations produce those sounds. Same kind of funky thing you can do with a garden hose. Next time you got your garden hose out, you ever do this? You kink the garden hose and then you unkink it. Try that next time. You unkink the garden hose and you hear a little squealing going on in there as you unkink it. That's a Fennigkoh sound effectively from the garden hose because of that same exact concept. And typically the sound, when the first sound is heard, that first Fennigkoh sound, the clinician is supposed to correlate that, associate that sound with the number on the gauge, give them the systolic pressure. Sounds get louder and louder, and when they disappear, they're going to associate that last sound with the diastolic pressure. Just another illustration of the same thing. We pump the cuff way up, pinch the blood vessel off, gradually release it, and then when the blood flow cuff or artery is completely open, you're not hearing anything anymore because there's no more turbulent flow at that point. Body abhors turbulent flow in vessels like that. Okay, I don't know if this will come through or not, but if you've ever noticed or sometimes watch when they're taking your own pressure this way to pump the cuff up above systolic. This rate of descent, 2 to 3 millimeters a second, is really crucial as well. If you go too fast, too slow, that creates errors, we'll see. Yeah, that'd be a good pressure. If you had that pressure, you'd like that, wouldn't you? No meds for you if that was the case. Okay, and this is the key. This type of indirect measure, or really, and this applies to virtually all of science, indirect measures give us just an estimate. So the misnomer comes, I'm going to measure your blood pressure. Well, you know, if you want to be an anal, like we all kind of are, we're kind of geeky, anal pinched, you know, linear. That's not really true. We're not really measuring pressure. It's an estimate, and it's precisely the reason why it may or may not agree with what we measure directly with an arterial line. Okay. So to be technically, semantically correct, we're getting an estimate of your blood pressure this way. So you can see why that is. Again, we're simply detecting the presence and absence of blood flow. Flow is not pressure. But why it works, we'll see a little bit. But that the top straight line is the pressure in the cuff. The corresponding curve right below is the arterial blood pressure. And if we time it right, this is why timing is critical. We'll get the peak systolic pressure when we hear that first sound. When the sound disappears, we get our diastolic pressure. And that's why on that last example, you heard the sounds getting louder and louder as we approached the mean there. Whole bunch of things that can affect the accuracy of these measurements. And this is where some of the criticism in the medical literature comes from, why these these other authors have been so critical of how we take blood pressure, because there's a whole host of things that can screw this up. Cuff size, we're going to see the significance of that in a bit. Positioning of the cuff, how tightly it's initially attached. If you have a real loosely attached cuff, that can create problems. You know, these aneroid, the gauges, you've seen how these things get banged around. They're thrown in drawers, they fall on the floor. You know, they're getting all banged up, whacked out, and they can get out of calibration quite easily. Even the oscillometric devices, if they haven't been calibrated or validated properly, leaks, stethoscope quality, real cheap qualities are going to have some filtering effects. Those carotid cuff sounds, which are pretty low frequency sounds, they can be in the 20 to 40 hertz range. So any clinicians that have, if you've got some compromised low frequency deficits, you could in all likelihood be missing those sounds. Okay. But technique, clinicians that if they go too fast or too slow, the general guidelines are about 2 to 3 millimeters per second. You can miss those peaks. There's also things called expectation bias or digit preference, where they just might round things to the nearest 5 millimeters, or they just think everybody is 120-ish over 80-ish. So that's where this expectation, they might just have an unconscious bias about what they think it should be. Distractions can be factors. And then of course on the patient side, yakking away, not a good thing to do. White coat effect, that's a very real phenomena. You know, people just, without even maybe having any awareness that they're anxious, just being in the presence of a exam room or something, especially if you're waiting for a half an hour and you're all half pissed off now, that can actually exacerbate things. So your pressure might be a little bit more elevated. But alcohol, caffeine, smoking, if you really have to go bad and you're holding it, that can alter things as well. So there's a whole host of all of these different factors that can influence the accuracy of these non-invasive measurements. But going back to the cuff size, and this one often receives a lot of criticism in the literature, and it's one that a lot of clinicians just don't seem to be aware of, the importance of the width of the cuff, the ratio of that width to the circumference of the arm. If you've got a mismatched cuff to arm, so you got a big Arnold Schwarzenegger guy, at 20, 30-inch biceps, and you try to use a regular size cuff, you're going to get artificially elevated blood pressures. So even though the person may not have high blood pressure, may not be hypertensive or even pre-hypertensive, the wrong size cuff can create that illusion that they have higher pressure. And the converse is also true. If you've got a young, small person, frail elderly person with a standard adult cuff, now that ratio is going to be too large, and you're going to get artificially lower than normal blood pressures. And they might say, well, I always had low blood pressure. Well, they indeed may have had low blood pressure, but it also could be artificially reduced by the inappropriate cuff size. And the general recommendations for the ratios out there are about 0.4, 40, 37, 40 some percent. So the width of the cuff, and it's the bladder, not the full width of the blood pressure cuff itself with the case on it. The bladder width divided by the circumference of the arm. If that's around 0.4-ish to 0.5, you're generally in good shape. Okay. So the advantages, of course, non-invasive, quick to do. There's reasonably good correlation. We're going to define this in a minute with direct measurement. So this is one of the reasons we keep using it, because of its relative ease of use. Downside, of course, noisy environments. You can get a lot of variability among different users. Same pressure measured by 2 or 3 different people, you can get 2 or 3 different numbers. Cuff size is important, and it can be more problematic on people with very low blood pressure, hypotensive, and infants. Can be a little bit harder to get good pressures. But correlation, when we use correlation in science, that has a very, very precise meaning. So you want to be careful when you throw around the word correlation, because when I hear that statistically, I'm thinking of a metric, a statistic. It's called an R value. It's a number, lowercase r, Pearson's correlation coefficient, lowercase r, and mathematically it gets a little chewy on how it's calculated, but fundamentally it's a number that's constrained to be between -1 and +1. And why it's meaningful is that it tells us about the direction and strength of a linear relationship between two variables. Like your height and weight, for example, is correlated. It doesn't mean one causes the other, but it means that height is often correlated with weight or vice versa. And so what we have here with these data, the scatter plot here, R of 0.5, you can see that the ideal is that line, that because it's a positive number, it's telling us we've got a positive slope. So an increasing X value results in an increasing Y value. And these are the actual data points. It's not all that great. 0.8, it's a much stronger correlation now. Okay? And then similarly, if the closer R is to 0, that's saying there's no relationship at all. If you had Ohm's law up here, where you had current and voltage, because it's a law, it's not up for debate, you'd have a correlation of 1.0. Current is perfectly correlated with voltage across a resistor. Okay? And the significance of that, again, from the literature, from studies where they actually measured arterial blood pressure directly, simultaneously with the cuff methods, they get correlations of between 0.7 to 0.8. It's not terribly bad, but all of those error factors, cuff size, all of that other stuff, all of that introduces variability that reduces R. So cuff size, technique, hearing acuity, all of those confounders collectively have the net effect of reducing that relationship. So under almost optimal conditions, we're about 0.7 to 0.8. Okay? So that's why we use the indirect cuff methods, because it's kind of good. No, it's reasonably good. Okay. The oscillometric method, you've seen these things around also, even in the grocery stores, Walgreens, they'll have these things in here. This is also an indirect method, also giving us an estimate. The main benefits of this machine, obviously, though, is that it's not using a stethoscope, for one, and it also has also controls the inflation and the deflation rates very precisely to eliminate another source of variability that way. And it still produces the same vibrations in the cuff, same Karat's cough sounds, but now those vibrations are transmitted to the cuff as pressure fluctuations. So the machine is actually picking up pressure fluctuations here, and it's from those pressure fluctuations and their magnitudes that the machine will derive and display systolic, diastolic pressures. Regardless of the machines, because they all have supposedly proprietary algorithms in there that my systolic is better than your systolic, they got all of that stuff going on. Regardless of the machine, the mean is always at the maximum of those pressure fluctuations. So this is what you kind of get. And of course, these can be set up to take pressures, periodically as well. So it's still an indirect method, still giving us an estimate, but it reduces some of the variability associated with stethoscopes. Okay. And then lastly, the invasive methods, which are direct measures. So when we cannulate an artery, we're actually with a transducer, we're actually physically measuring blood pressure. So this would be an appropriate use of the term blood pressure measurements, is when you cannulate that artery. And so you hear this is an A line. I don't even know if some places are still doing pulmonary artery catheters. Are you guys still seeing those done? Maybe not, some still. If you see a heart line, you see any, on the neck, swan lines in it anymore? Still do that? Depending on, yeah. So if you see a big 4x4 on a guy's neck, likely he has a pulmonary artery catheter in. But they all use the same transducer, whether you're using intracranial pressure, we're measuring pressure. And to measure pressure, we use transducers. And just like all of our other transducers, it converts basically one form of energy into another. All transducers behave essentially that way. Regardless of what the input might be, we can virtually measure most anything out there. And our outputs of these transducers are typically, not always, but more often than not, voltages that correspond to the input value. And The good transducers, they're virtually perfect in that regard. Correlations are almost 1.0, very linear, very repeatable devices, the good ones are. Okay. And if you remember your old circuits from your old Wheatstone bridge, you remember that some of this stuff from way, way back? Fundamentally, what's going on in these things in a semiconductor are essentially resistive strain gauges of sorts that when a pressure is applied to those devices, some of the older devices had actually almost like a diving board cantilever design in there, where they had a semiconductor, a piece of silicon, they'd have resistors etched on the top board of the board, 2 resistors etched on the bottom, and the pressure as it was applied at the end of the diving board basically changes the length and the area of the strain element, like pulling on a piece of taffy. You know, the length changes and the area gets smaller. Combined, those changes in resistance produce corresponding changes and produce a voltage change. So fundamentally, they kind of work really slick that way. Okay. And then the basic components of the system are kind of unique too. We obviously have the monitor, the transducer. We don't typically use pole mounted. You guys, we don't use pole mounted transducers. Do you see some of those? Cath lab, they're still using them on the pole. Because yeah, you can't get at, yeah. So the transducer connected to the monitor, and oftentimes we will have some kind of a, often type of heparinized, they still use heparinized saline to just to flush, because you have to, if we didn't do this, if we didn't keep a constant low, keep open rate of saline through that catheter, keep it patent, it would ultimately clot off. So we have to do that to keep that, help keep that catheter patent. We'll see. And that is a pressurized bag up there, because if our artery pressure, if you've got a mean pressure of 100 millimeters of mercury, the only way you're going to get fluid into a pressurized vessel is you have to have a pressure higher than what's inside the vessel. So we'll have to pressurize that bag to get that slow rate of saline in there. Okay. In the cath lab, especially where this becomes more, if the transducer is mounted on the wrist, not as critical, but we generally want that transducer to be right at the heart level or this plevostatic axis. If that transducer is too high or too low, that can artificially alter the measured pressure, because you're adding or subtracting an added fluid head to the transducer, and that can introduce error for us. Okay. In fact, this was probably at St. Luke's Day when I first got there a long time ago in the 80s somewhere. I made a hydraulic generator, a generator to generate a fluidic pressure, because we were evaluating transducers at the time. And to try to illustrate this concept, these direct pressure monitoring systems are what we call second order systems, because they ultimately would need a second order differential equation to fully describe what's going on. But it also indicates that it has 2 energy storage elements in it, a compliance and another fluid analog to inductance, or inertance it's referred to. And fundamentally what that can do, it can create a resonant, all second order systems have a resonant frequency associated with it. And the significance of that we'll see in a bit, in that here is the input pressure signal going into the pressure transducer. So you got a constant amplitude signal here. So this could be 120/80, say equivalent blood pressure. All I did here was increase the frequency, didn't adjust the amplitude at all, just the frequency of the signal. And as this frequency of the signal approached the system's resonance, you can see what happened, how artificially it got bigger. And the significance of that clinically is what that's going to do. It's going to distort the snot out of the real blood pressure. It's going to artificially elevate systolic, reduce diastolic pressure. It's going to distort the signal, the very signal that you're trying to measure, okay, at this resonance. The same kind of, any system that has mass, elasticity, or compliance, and some kind of inertia to it will have a second order system. So loudspeakers have natural resonant frequencies to it. And if the speaker enclosure, for example, happened to resonate at 100 hertz, an incoming sound with frequency components at 100 hertz are going to be artificially amplified. So the speaker is going to sound louder at 100 hertz than the actual the incoming sound. Some people might like that, you know, give me some of that bass, you know, but it's actually a distortion in a sense. Same kind of thing happens in our series RLC circuits. You remember that from somewhere way back in the old days? Okay, but when you got a series RLC, because we got two storage elements, an inductor and a capacitor there, and at resonance, when this generator here is at the resonant frequency, 1/2 pi FC, the inductor and the capacitor electrically essentially cancel themselves out. So you'd end up with a maximum current flow in that circuit at resonance. Okay, not a good thing. But an optimally a good arterial waveform, and you can just do this qualitatively. You don't got to get involved in no differential equation. You're not going to do anything like that. But just qualitatively, if you see a nice distinct dichrotic notch, again, this indicates closure of the aortic valve. And if you were doing this on the right side, the waveforms are very, very similar on the right side of the heart, leaving the right ventricle, because when the pulmonary valve shuts, you also get a notch. That's just the pressure magnitudes are typically less on the right side, but the morphology are very similar. So you want a nice distinct dichrotic notch, very distinct rising edge, nice clean crisp waveform. So if you see that, that's almost all you generally need to know, that you've got a relatively good optimized, it's called critically damped engineering wise. So, and one of the ways in which you can test that, if you still have the transducers with the little pigtails on it, we'll see one in a bit here, but what you can do by pulling, you don't do it, only the clinicians should be doing it, you pull that little pigtail and you let it go, it introduces a step or an impulse function into the system. And so you got a pulse here, maybe 300 millimeters of mercury, a small little bolus of fluid, and you can measure, looking at the response, how does the system respond to that impulse? And if you only get maybe one little oscillation in there, that's typically the hallmark of a good critically damped system. The suspensions in your cars. If you got a good, well-balanced, tuned suspension, you hit a pothole and you're okay. If you got a car, an old beater with a bunch of busted shocks, so all you have is a mass and a spring, right? You hit a pothole and you go boing, you're gonna be bouncing around all over the place. So a good optimally damped system will have only a very short oscillation to it. And that's a little, do you guys see these yet? Is this stuff still out there in your transducers if you look at it? Okay. Biomed guys, you never want to be the one to do that. You can get yourself in some really hot ass ice water, because you're effectively administering a bolus of heparinized saline. So only the clinicians should do that. You can suggest that they do it if you strongly suggest or suspect that this system has got some issues associated with it. You can have them do that fast flush test, because I don't know how often the nurses, they might be trained to really understand what it is they're trying to do when they do that particular test. But you can definitely recommend that it be done, and you can then qualitatively start to use that information to potentially troubleshoot a faulty system. Okay, if it was underdamped, you're going to see all kinds of artifact where the dichrotic notch should be, because there's only one of them, not a bunch of garbage in there, and you'll see a lot of ringing, classic ringing here. It's a hallmark of an underdamped system. Again, that's the car with the bad shocks oscillating it that way. And it's kind of somewhat, in the classic tip-offs, you're going to have much narrower systolic peaks are going to be overestimated, and the monitor will display larger than typically what should be systolic pressures. The dichrotic notch will be exaggerated, and but the mean is still the same. So the mean is relatively immune from these resonance issues. So, and some of the very same things we always typically want in a pressure monitoring system can actually contribute to these underdamped systems. More often than not, I don't think we tend to see underdamped systems as much as we see the overdamped case. Overdamped cases are more often likely, and the classic things you see here. Systolic pressures are going to be lower. Diastolic pressures are going to be larger than they really are. And the dicrotic notch is almost going to be absent. So you've got a grossly overdamped system. Where'd the notch go? Okay, and you can see you start to lose some high frequency response here as well. And oftentimes, air bubbles. And they can just be these little teeny micro bubbles. You got stopcocks. Anytime you've got discontinuities with tubing, stopcocks, all that other jazz in there, you can get little teeny baby bubbles congregating around this stuff. And you remember your circuits, how capacitors add in parallel? 1 microfarad in parallel with 1 gives you 2. These little baby air bubbles, they behave like capacitors. So if you got 100 little air bubbles in there, it looks like one great big ass air bubble. The fluidically, it looks like that. So that can create these kind of issues. So even though they might appear very small and benign, collectively they can contribute to overdamped systems like that. Okay. So bottom line, the takeaway is to keep in mind that these indirect methods, as good as they are, they're not going to ever go away. They're just simply an estimate. So if you get complaints of why the cuff doesn't equal the direct, well, because they're different. So and it's up to the clinicians to clearly the direct method, if it's done correctly, lines well preserved, maintained, it's going to be the most accurate of the measurements. But this is just an estimate. So it's beginning and ending of turbulent blood flow, very sensitive to cuff size. Unfortunately, some of the manufacturers, they've gotten wise to this in that if you look at the extent of the Velcro covering on the cuffs, if the cuff is not the right size, it just simply won't, there's no Velcro. So that's kind of the way of saying, well, I guess I got the wrong size cuff. So, but that's fundamentally it. So it makes some sense, kind of, a little bit. Okay, that's all I got. Yeah. Again, thanks for being here, and hope there were little bits and pieces of this that maybe filled in some gaps for you along the way. See what happens, huh? Oh, with the assist devices. So with the continuous flow. Ah. They give you a reading, one number, that number of Oh, yeah, that's a good point. But that's interesting. So do we even rely on the mean? Well, it does. They give a mean, that's what they'll put down. Mean, probably not. Do a manual. Then listen for the one. All you can hear is really one swoosh instead of systolic diastolic. Ah. Because that's a real funky thing, isn't it? Yeah. First time you hear that. I remember seeing when this first, the first totally implantable heart was done. Some guy, Mr. Toole or something, the very first one that was done, and that's all you could hear was a whining in the chest. And that was just wigging the clinicians out big time. Like, what is that? It's a very bizarre thing to get. I think back in the early days of the Jarvix, you remember those days, how it was just so foreign and abstract, the waveforms and stuff. So, yeah. They're still using it. Really? We haven't done it for years, but we still use it. Wow. Except it doesn't use the scuba tank. Oh. Okay. But it's the same basic design, with the Velcro sticking there. And I got something that kind of works, I guess. Why not, huh? Yeah. Okay. Any other questions or issues on this stuff or anything I may have missed or I got screwed up? Do you see anything in there? Correlation of 7 to 0.7 to 0.8, is that under ideal conditions or is that under average? It's under more controlled conditions. So yeah, that might be about the best it's going to get in that range. And another very significant related statistic to that, if you take R and you square it, We call it R squared statistically. So, and it's called the coefficient of determination. And what that tells you, like say if you had 0.7, if you squared that, you get 0.49. 7 times 7 is 49. All that tells you is that 49, what that's telling you further is that 49% of the variability you're seeing in the cuff method is explained by the direct method. So the question that further begs is, well, what's causing the other 51% of the variability? So if you're at 0.8, for example, 8 times 8 is 64. Only 64% of the variability in the cuff pressure is explained by the direct method. So 36% is caused by a whole bunch of other junk. And that's what we call confounding variables in science and in research, is that it's like putting a little drop of black paint in a white paint. You know, it's just a bunch of mush. You don't really know what's causing it. So that's why anything we can try to control, that's why we try to control variables in science as much as we can to maximize R squared, to get as much explained variability as we can. But yeah, the 0.7 to 0.8, that's what the early research has shown. That's about as good as it's going to get. You know? And you know, and that could translate to 10 plus more millimeters. That could put somebody from a hypertensive pre-hypertensive into getting meds. You know, so a lot of things to be aware of. You know, and we don't often want to go too over the deep end anally with this stuff, which we tend to like to do. I can't tell you how nuts I get. We got students sometimes on lab reports, you know, calculate a heart rate. One time specifically, maybe we had them just take a heart rate off of a strip. You know, and I don't know what they calculated. One time got ridiculous. They get 100.286595555528 beats per minute. You got 8 decimal places to a heart rate. And I go ape shit. I thought, and I would write with my red pen, you know, limit your number of decimal places to a meaningful level. And I'd see it over and over and over and over and over again. And then I finally got the big white mark red board. And I ultimately made a stamp. This is no kidding. I got so sick and tired of writing the same damn comments. I got a stamp made. I said, you people cannot leave this school talking like that. You tell a doc the pressure is 1.899556268 beats. Yeah. You went to MSOE, didn't you? That's what. But yeah, you don't want to think like that. It drives me freaking nuts. You know, but the calculators did that. Excel, notorious, defaults to 12 decimal places. Yeah, but anyhow, you don't want to do that. But and it still doesn't work. We had senior design shows in spring. Big public presentations. You remember those days? Big public presentations. Here, the students got 48 decimal places. Thinking, oh shit. One time we had, you know, we do these little circuit labs with little 1/4 watt resistors. You know, little 5 volts and stuff. And the fact that I was in one room and the circuits guy was on the other side of the room, and he asked the student what the power being dissipated by the resistor was. Oh, it comes out to like 4,028 watts. And I heard on the wall, the faculty was beating his head against the blackboard. Like, oh God, where did I go wrong? I mean, it just, I don't know. In fact, I had a USB microscope in the same similar lab that I set up in a 1/4 watt resistor. And I purposely burnt the shit out of it. I overdrove it, you know, to emphasize V squared over R. You remember that one? Power is V squared dissipated over R. And because invariably, Dave maybe remembers that too. You walk into the lab and you get that stink of burnt carbon, you know? Yeah. And of course, nobody wants to own it. You know, it's like farting in the elevator. I didn't do it, you know. But that smell, I believe it's very diagnostic. Well, you guys remember, if you're serving some electronic and you get that stink, that burnt phenolic stink, because yeah. So it's meaningful. So I burnt the resistor up and I projected it right on the screen. You could see the thing getting brown. Then I said, come here and smell this stuff. You know, take a snort of that. This is so. And of course, they think I'm weird, but I don't know. I'll try to get the point across. You know? So.
Walked up to a piece of machinery they told me was broke, and I go, yep, you burnt
Yeah, see, a transformer, the varnish, the windings, you can stink, you know. So yeah, no, that's small meaning. We don't teach that stuff. You know, you guys find it out the hard way, or you learned it a good way. But in a typical engineering school, it's all math, and you're doing some calculus shit on stuff, and yeah, you know, then the kids leave, they don't know what it is. But anyway, I think we're good on time. So again, appreciate you being here, and we got to sign a little form, I guess, and we'll do it again, huh? Okay, good. Thanks.